So, good morning, everybody. It's time for that last QBI lecture. And today, it's not so much about how to process the pixels themselves, but more frameworks, how to work with large data. And this is much about computer science. And you will see, no, it didn't work. Oh, so it works. Wait. Again, the usual problem. So now, there is a lot of material about big data. Some from Google, they are doing it a lot. Then there are scalable systems courses here at ETH and all over the world in different universities. You can also look at a tutorial about Hadoop, which is a framework for doing this massive processing. And then there is also a course on Introduction to Data Science, where you can see also more material about big data and how to process this data. Another thing is cluster computing, is when our computer is not, a single computer is not sufficient, then there are also a lot of methods how to bundle up several computers and let them work together. And there is also available resources here at ETH. And one of them is called Condor. And this is the available resources and how to work with it. Next thing is also a thing how to manage all this data that we produce. And let's see, it was a couple of weeks ago, I talked about Pandas, which is a kind of a database, but this is more server-based database tools for massive processing. Cloud computing is the thing when you have outside, when your cluster is not enough or you don't have a cluster, then you can buy in on remote resources. And Amazon S3 is one big cloud service. There are also other ones and a couple of papers here to look at in this topic. So today's topic, we have some computer science principles, what is parallelism, how to work with distributed computing, etc. Then also how this is organized in the whole framework, queue systems, cluster computing, how that works. Then we go on to big data and tools for how to work with big data and cloud computing and what happens beyond that. So we already have talked about, we have a lot of data. Maybe we can get some of it in our memory for processing, but often we can't do it. And computers with more than 256 gigabytes on board is quite expensive and not always so easy to get the hands on. Maybe your group is investing in some workstations like this, but it's usually not the case. And if you would have this amount of memory in your computer and would split it up on, say, 16 cores, that would be 16 gigabytes per CPU. And when you consider that a gigavoxel image, which is not uncommon, it's more also going towards the 8 gigavoxel, so that would be 2K cubed. Then you would only have a single image in memory at the same time per CPU. So you have to come up with some idea how to handle that. This also points out that a normal laptop, which if it's well equipped, maybe today have 32 gigabytes of RAM, but that is more the exception in the high-end systems. It's more likely that you have 8 or 16 gigabytes. Another problem that you can have is the speed of your hard drives and also network access and how quick you can transfer the data between different nodes. And that is actually a bottleneck in many computational systems. Last thing, what you also have to consider is redundancy and safety if one computer would crash on the way or make a bug that doesn't produce the right result. What happens? Do you have to rerun everything, or did you lose what you had done, etc.? Then we also, on top of it, we don't only have large single data, but we also have many. So if you want to do, for example, a genome scale studies, you need thousands of samples in order to get the right statistics, because usually you want to look at the very tiny outliers in this data set. And you need to analyze all these data sets identically, not doing it arbitrary for each sample. Then if we also go on that we have dynamic experiments or even bimodal experiments combined, then it gets even worse. And you really need a lot of data when you do this kind of, particularly when you do genomic studies. And it seems like radiologists in Switzerland apparently make 1 petabyte of scans per year. And handling all that data is quite tough, actually. Then if we do exploratory studies, then we know something has happened, but we don't know exactly what. So we have to also be more flexible in that case. And then we need the flexibility to be able to develop new analysis easily. So here is one example. It's a zebrafish, and you want to look at this animal in cell scale levels. That means we have imaged this fish at 0.74 micron resolution, and the images are 11K by almost 3K by 1K, more or less, and that would give us about 20 to 40 gigavoxels per sample. And then you have to scale up that with the number of bytes needed for the computational precision. So it can easily be 4 or 8 times more data. And what they want to know is they want to do identification on the single cell level. So it's not possible to downsample this data. And what they want to know is the cell network and how they are connected, and also classification of cell types in the fish. And this should be also registered with the histology of the animal. So here you see also the volume that I'm browsing through. I thought it's not in loop, okay. So there we can see it again. So this is the 20 to 40 gigavoxel image in a very compacted form. So this is quite a challenge to get through. You can also look at the brain project, the whole brain at cellular resolution. And here, 1 cubic centimeter is stepwise scanned with 1 micron resolution. That also gives us 1,000 gigavoxels per brain sample. And here we also need a registration task to get all these subvolumes to match up. And what they want to look at is the blood vessel structure and networks, and ideally also combine it with functional MRI and histology information. So that's also quite a challenging task to handle all this data. So what is wrong with the usual approaches? We have an initial workflow, want to filter, maybe some medium filter to get rid of some outliers or noise. And that would be on the slice, a 5x5 kernel should apparently be enough. Then we want to apply a threshold of 10. So you actually have the code, down here. And then we want to label these components, and finally looking at how many voxels are in each component of this data. And then we want to write the data out. So looks like a quite straightforward little program to do. And the problem here is that it's not so easy maybe to change the workflow. So maybe you want to check what is the difference between the code, the output if you use a Gaussian filter instead of a median filter. Or maybe you want to upgrade it into 3D instead of 2D, which makes sense when you work with three-dimensional data. You always should look at what happens up and down of the current slice. And then maybe you want to do mass production, looking at doing the same analysis on all images in a folder. Then you also have to do some looping. So if you start here with a bad starting point or a bad design, you can have difficulties of getting it right. And it already starts actually on how you organize your data, how easy it is to handle in the processing. So what we need to take care of is to make sure that we have a good concept for big data and also reproducibility. And that should be actually considered from the very start of your planning, maybe even at experiment time, because that's the time when you produce and put the data in different folders. And now we are going to switch over to some computer science principles. And these topics we are going to talk about is parallelism, what it is, distributed computing, resource contention, if we have shared memory, race conditions, synchronization problems, deadlock. Actually, all these come together in a big bunch of problems. And then there are also two ways of program, imperative and declarative. So first, what is parallelism? Parallelism is when you can divide a task into several subtasks, and each of them can be worked on at the same time somehow. So the example is you want to walk 5 minutes, and you also want to talk on the phone for 5 minutes. If you do these tasks in series, then you first do the walking, and then you do the talking. Good. But it's not very efficient because it takes 10 minutes. And if you instead could do this in parallel, then you possibly could do walking and talking in 5 minutes. Maybe you slow down a little bit because you have to concentrate on what you're talking about, but you can definitely do it in shorter time than 10 minutes. In distributed computing, we are actually going away. So the parallel computing is essentially just on the CPU level to begin with, at least. In distributed computing, you're talking more about distributing the tasks on different computers. If it is in a cluster or if it's in a cloud, it doesn't matter. But it means that you can parallel process much more powerful. And here we have some problems to think about. We can have network delays because all these nodes in the computer network, they need to talk to each other. We can also have file system issues that the hard drives are not responding fast enough and providing the data. And there could also be other people on the system. So you're not alone on this cluster. And then you have to somehow organize that you have different priorities in the processing. And these things, they can actually become a major problem in your processing. And here are some examples of distributed computings. And let's say you have 10 friends and they all know together, the common knowledge is they know all the capitals in the world. And if you want to know the capital of every single country, you just yell out to all 10, tell me the city. And that's, and of course, wait till someone comes with a response. And that's an ideal task for distributed computing. And to find out who knows the most capital cities, then you have to actually ask each one of them and see what they tell, how many they get back, and then you can select afterwards which one knows most. And that's a not too bad distributed computing task. However, if you're going to each friend has some money and you want to go to them and ask how much money do they have, then you have to ask everybody and then you have to sum it up afterwards. That's not so good. And if you even want to know the median value of each one, then there is a lot of overhead programming and you're going down in the efficiency of this distributed computing task. And one problem when you do this, actually parallel programming, distributed computing doesn't matter, but there is always problems with resources. The data is stored in memory or in files. You can have pieces of information, you can have different network resources. And a problem that can come up is a so-called deadlock. And that is when several people want to access the same resource and only one at a time can have it. And a classic example to describe the deadlock is the dining philosopher's problem, where you have a couple of philosophers sitting around a table, and between them, they have only one fork. And to eat, they need 2 forks. Now is the question, who can eat first? And then they start, everybody tries to grab. Oh, everybody only got 1 fork. I can't do anything. Then they have to go back, trying to solve the problem and make sure that they can actually handle the case that everybody can eat at some point. And that is a priority race condition that somehow there must be a scheduler that tells, now you can do it, now you can do it, now you can do it. Otherwise, it doesn't work. And the philosophers, they're probably trying to find the philosophy of each era they come from, and that can take time. And that's the so-called deadlock. And what we have, there are a couple of challenges now when we do this parallel processing. And sometimes you have to do a lot of coordination between different computers when there are tasks that are not so easy or so obviously parallelizable. And the other thing is that mutability is when you have done some processing into processes and you want to write it, and it appears that both want to write on the same memory spot. Which information is the right one? Which one should be done or which one should not? And to be able to handle that, you actually also have to set some barrier mechanisms to protect against it. And that is, you have to have something called, for example, semaphores or mutexes, that you say, in this area, to access it, you have to take your ticket and stand in line to be able to process or to change this value. And so these are, of course, things that can be done, but it's easy to come in the deadlock situation, because if you have mutexes that are interleaved in weird ways, can unfortunately easily happen, then someone has taken that ticket and someone has taken that ticket, and they're both waiting for each other, and then nothing happens. Oh, this one should be possible to run. Yeah, there it is. Oops, sorry. So what can happen is in the beginning, you can have a quite good speed up, but at some point there is some overhead caused by the implementation, available resources, and scheduling. And all of a sudden, you don't have the linear scale up that you would like to have, but it can even be that you're going back in efficiency because of these collisions and waiting situations, etc. This is just a hypothetical plotting of what could happen. And here you have the blue line is the ideal speed up, and the, what is it, purple line is the real speed that you get. And in a real life situation, This is actually a performance test I did on code I wrote. Here you can see a way to spot different hotspots in your code. And it's quite obvious that we have something here called ring cleaning, which takes very large amount of the processing time. So this would be an ideal target for introducing parallelism. And that is what I did. And afterwards, you can see that this was reduced radically, and the total processing time was reduced to about 1/3 or something for the 1K case. So this was an obvious case where the parallelism could actually bring a lot. Other pieces of the code were actually already parallelized. So like this one and also that one, they are already parallel. So that was the kind of last missing piece that I needed to squeeze down. But it visualizes how much you can bring down by just splitting up the code on different cores. So this was just local computing on this, on a single computer. The theoretical speedup you can expect is described by Amdahl's law, and the code has different components. One is sequential, can only be executed in sequence, and one part is parallelizable. And this equation here gives the so-called latency. And after a while, you can see actually that this one converges to a plateau, because then it's essentially only this part here that is determining how long time it takes. So if you divide this P by 1,000 or 10,000, it's just getting smaller and smaller and doesn't bring much contribution to the whole speed up effect. So what we can see here in my code example is I have one piece that is nicely parallelizable, and one piece which is here labeled others, that's actually reading and writing the data. Takes quite a lot of time. And that part can, with limited possibilities, be also brought in parallel. There are ways to solve it, which can be handled, but in general, it's in principle that this is a static piece. Unless you change your hard drive, this one will not change. And if you would have the data on, for example, the network on a shared server, then this piece would be even larger. And then it doesn't matter how much you bring in, time you bring into optimizing this part, because this one is anyway the dominating and you can't get around it. Then when we change to the distributed computing, then we have the task of sending out instructions and having data far away. It could be that you have a central server somewhere, maybe in Ticino, here in Switzerland, where we have the big computing center. And you also need to send some instructions how to handle it. What you also have, if you have, say, 1,000 computers working in parallel, then you also have to have some redundancy, fault tolerance, if one computer fails in the computation, so that you actually have error checks somehow to make sure that you know that, okay, that one didn't work, then we have to do that task again. And then we also have the storage problem that if you have the data somewhere, it always takes some time to get it to your point. And it could be that you have very good network connections, but it's not sure that you have it all the way. And you need a very big data pipeline to assure that you have really the good speed effects of your transfer. Ideally, you can send the data to somewhere and then it's processed on that place, but you can't always rely on that. When you program, you can program according to different paradigms. One is imperative programming. That is the type of programming you learn at the beginning. It's supported by most languages. So you have C, C++, Java, MATLAB, Python, and so on. And here you more or less give the recipe, do this, do that, do this. If not, do that, etc., etc. So for example, we want to make a soup, and here we have the tasks. First, we buy the vegetables because we need to have something to cook with. Then we buy the meat at the butcher's. Then we chop the carrots into pieces. And then comes the potatoes, and we heat water. Then we have to wait until the water is boiling, until we can put in the veggies. And finally, wait another 5 minutes, and then we add the meat and then let it boil until the meat is tender. In declarative programming, it's a bit different. That is used in, for example, in languages like SQL, Erlang, Haskell, Scala. Python can also do it, and R if you want to. And here, you make up some kind of set of rules or goals that you want to achieve instead of exactly command, do this, do that. And the data is then in this framework is scheduled, automatically managed, and then the scheduling can be automatic or is automatic, but depending on how good scheduler you have, it's not always efficient. Here, the making of soup is that we declare some tasks. So first task is buy the vegetables at the market. That's the task shop veggies. Buy the meat at the butcher, and shop meat is that task. And then we start to declare what we want to do. So here we say, wait for shop veggies. And when that is done, then we can start next task. And that would be chop the carrots. And here also, this could be chop the potatoes. And then we can start the task heat water. And finally, we can put everything together here as wait for boiling water, chopped carrots, chopped potatoes. And then with that, we should add the chopped vegetables. And finally, wait another time, 5 minutes to add meat. Looks maybe a bit complicated, but here we have declared specific tasks. And these tasks that we have declared can be sent to different CPUs or processing units, and they can be handled. And then the scheduler just waits for the signals to come back. Okay, I have the data, then I can send that task away. For single CPU, doesn't make sense. That's too complicated. But as soon as you have more cores or more computing units, it makes sense to do it like this. And yeah, that was more or less this slide. In particular, if you want to do the imperative soup faster, that would be that you have more people. Everybody are chopping the carrots or chopping the potatoes. So everybody are doing it in one at the same time. That could be you get a sack of potatoes, you get a sack of potatoes, and you get one. And when you're done, then we are finished. And the declarative case, of course, then we can, as I said before, just give each one of these tasks and wait for them to finish. So what we can do is in imperative, we can optimize specific tasks and making them faster, making them more efficient. For example, we have the MATLAB Python way of doing the fast Fourier transform, is that there is already a library function that does this, and it's optimized to do it very fast, and that's good for finishing that step. And if we have many soups at the same time, could also be a way that we actually boil soup 1, 2, 3, and 4 and run them in parallel. And that would lead us into some kind of cluster-based processing. The parallel is that you have maybe 1,000 images. You do the same thing. Image 1, 2, 3, 4 is sent to each one of the nodes, and finally you have the result. In the declarative case, we would run everything at once, start all the tasks, and let them wait for each other. Each computer gets a task which it runs, and the actual execution order doesn't really matter. It's only when they come to this barrier point where they have to wait that there is maybe some dependency that could be delaying the problem. What we also can think about is doing lazy evaluation. That means don't do anything until you need to do it. And that could be that, let's say you have some, what was now in the soup? Let's say we have, we need to have the vegetables before we can start the boiling. Okay, but then we don't do that part. We don't wait. We're just standing in an idle loop. And then when it comes, then it starts doing stuff. And for example, here is an example, never buy tomatoes since they are not needed in final soup. So that would be, if you would have a process for buying tomatoes, it would never be called. Organization is also very important. I mentioned it in the beginning today. And often it's very important that you organize your data in the right way. Also, the results organized in the right way, because sometimes it makes sense to store the data in the tables in a certain structure when you process it in step 1. But in step 2, it may not be very efficient to have it like that, and you have to have very awkward ways of extracting the data. So it's important that you have organized your data in the right way in raw data format, but also when you do it in the intermediate steps, and when you want to plot results, etc. So in my case, I have somehow realized that instead of doing fantastic data structures, I more or less just dump everything in a large table. And then I have to use database access, for example, in Pandas or in SQL, do some filtering of the data, and then I get what I want. That's usually the most efficient, but in my experience. So cube computing is actually a managing method of many tasks. So I mentioned that you're not alone on the computer system, and somehow you have to have someone that tells when can you or someone else do the processing. And what we have in the system is we have the resources, which are computer, memory, storage, etc. And it's available to some degree, but not all the time. So you have to make sure that everybody gets their piece of the resource. The jobs are the tasks that people want to run. Could be different sizes, different lengths, different requirements. And when you submit a job, you should also include expected, or actually the code will add expected execution time of this code. That makes it possible to schedule the whole thing. And finally, we have the users who submit their jobs to the system. And it's often not desirable that one user gets supreme access to the whole system at once, but it's mostly interleaved that everybody reaches some final delivery time, which is realistic for everybody. This is quite a big task for the people who are managing these computer systems, to make sure that this task handling with the resources and the users, that ends up in something that provides a service to everybody. A cluster has a structure which is based on, we have some master nodes or name nodes. That is the access point where you go to and submit your tasks. You never see the small ones behind it, but this one is the one that dispatches the tasks. So when you log into a cluster, this is what you see. Then you have worker nodes. These are the ones that are actually doing the work. And yeah, you may see them as node 1, 2, 3, but you never really go into each individual node and do stuff on it. You shouldn't have to. Maybe if you are the one mastering the system, then of course you have to do it. Initially, when you're training, you may also look at it, but afterwards, you should more or less just say, I want to do this task, it should be split up in this way, and send it off. And then we have the scheduler, which could be a part of the master. That is the one that decides when should this task be executed and which resources it needs, etc. Time-wise, let's think. Yeah, let's do the databases too. So I have until now talked about different databases and ways to store the data. Usually what we want to work with are images. You can store images in databases in this context, but now let's just make some simple examples where you have, here you have animals, where you have an animal ID and you have a weight which is associated with it. Another example would be that we have different cells, and here we have a little bit more characteristic information. So first we have the animals. So these two are actually linked in some sense, that we have the animal ID, and here we also have animal ID, and we can see more information about this animal here. So it should be that the cell type in animal 1 is cancer, it's anisotropic, and it has a volume of 1, and so on. And with this, you can cross-relate these two tables and get information out in the way you need it, not to repeat information. So it could be that you have many cell measurements from animal 1, but some are cancer and some are healthy. Could be, but if you want to have that, you don't need to carry on all this weight information or names, etc., of the animal that you don't have to carry on in this table. That would be a waste of storage space. So that's why you have this relation between different tables. A typical language used to access databases is SQL. Actually, it's always written as SQL, but it's pronounced SQL. It's a structured query language, and it's actually quite universal. I think it's been around since, I think, even the 70s. So it's quite an old, well-used language for accessing databases. And here we have different libraries or forms. So there are SQLite, MySQL, and Hive. So there are different types of libraries, but the basic syntax is the same and the way how you write it. Typically, some query basics is you can select volume from the cell table. So here you say, select, I want the column of volume from the cell table, and then I get this information. Or if you want to get the average volume of all cancer cells, oops, now it's confused here, then you select first average volume, also volume, and computing the average from the cell type where you have the type equal to cancer, and then you get the average value of that. So this is a way how you can access a large database. It's quite rapid actually to get the information out of the database. It's very efficiently structured and it works well. So it's in a way, it's what we also did with the pandas data frames. And there are also more efficient data frames that you can work with. And pandas can even read in SQL data and you can work with it. If it fits in your memory, you can also read in data from SQL into a pandas data frame if you prefer to work with that. Then we can have even more advanced, it can be quite complicated, where we select on different criteria, and you can even join different tables, and then it gets really complicated. So you can actually extract very specific information from the databases using SQL. It's maybe not always so easily readable, but you can get efficient queries if you know how to do this. So some people are actually very specialized on working with SQL. Then you can go on. It's maybe not sufficient to work with a SQL on a single machine, but you may want to do connections between different databases and different connections between larger data sets, different tables, etc. And then you can do also counting and so on, like this here. It is maybe still readable, but it is not so easy to handle after a while. And one more thing, there are also vulnerabilities. So don't put too much SQL code in a web page, because someone can inject bad code in your queries by just adding some extra pieces. And then if you're unlucky, someone can actually kill your database by just inject the wrong SQL code. So be careful when you use SQL accesses in web pages. And then we want to add on to be larger, and then there are different more scalable databases. So that would be the so-called NoSQL or not only SQL. And that is for handling larger networks and graphs. So actually, personally, I haven't used this big databases, so I can't tell so much about it. But it's when you come into big data, you probably need to go into more large-scale databases to handle. So this would be the time to make a break. It's probably saying bing bong soon.